Essay 96, Chapter 1 of Principles of ECE, Basics of Cartan Geometry. Historical background. Geometry was equated with beauty by the ancient Greeks and was used by them to create art of the highest order. The Parthenon, for example, was built on principles of geometry and a deliberate flaw introduced so as not to offend the gods with perfection. 1,000 years later, the Book of Kells scaled the magnificent peak of insular Celtic art, using the principles of geometry to draw the fine triskells. Aristotelian thought dominated natural philosophy until Copernicus placed the sun at the centre of the solar system, a challenge to ecclesia, the dominant European power that had grown out of the beehive cells of remote places such as Scalig Vehil. In such places, civilization had clung on by its fingernails after the Roman Empire was swept away by vigorous peoples of the far north. They had their own type of geometry carved on the prows of their ships, interwoven patterns carved in wood. Copernicus offered a challenge to dogma, always a dangerous thing to do, and human nature never changes. Gradually a new enlightenment began to dawn with figures such as Galileo and Kepler at its centre. Leonardo da Vinci in the early Renaissance had sensed that nature is geometry and that one cannot do physics without mathematics. Earlier still, the Perpendicular and Gothic styles of architecture resulted in great European cathedrals built on geometry. For example, Cluny, Canterbury and Chartres. Both Leonardo and Descartes thought in terms of swirling whirlpools, reminiscent of Van Gogh's Starry Night. Francis Bacon thought that nature is the measuring stick of all theory and that dogma is ultimately discarded. This was another challenge to ecclesia. Galileo boldly asserted that the sun is at the centre of the solar system, as we call it today. That offended ecclesia, so he was put under house arrest but survived. It is dangerous to challenge dogma, to challenge the comfortable received wisdom which bypasses the need to think. So around 1600, as Bruno was burnt at the stake, Kepler began the laborious task of analysing the orbit of Mars. Tycho Brahe had finally given him the needed data. This is all described in Kessler's famous book, The Sleepwalkers. Kepler used the ancient thought in a new way. Geometry describes nature. Nature is geometry. The orbit of Mars was found to be an ellipse, not a circle, with the sun at one of its foci. After an immense amount of work, Kepler discovered 3 laws of planetary motion. These laws were synthesized by Newton in his theory of universal gravitation, later developed by many mathematicians such as Euler, Bernoulli, Laplace and Hamilton. All of these descriptions of nature rested on 3-dimensional space and time. The 3-dimensional space was that of Euclid, and time flowed forward on its own. Space and time were different entities, until Michelson and Morley carried out an experiment which overturned this dogma. It seemed that the speed of light c was independent of the direction in which it was measured. It seemed that c was an upper limit. A velocity v could not be added to c. Fitzgerald and Heaviside corresponded about this puzzling result, and Heaviside came close to resolving the contradiction. Lorentz swept away the dogma of 2,000 years by merging 3-dimensional space with time to create spacetime in 4 dimensions, ct, xyz. This was the beginning of the theory of special relativity. In transforming quantities from one frame to another, c remained constant, but t, x, y and z varied, so quantities in the new frame are C t tick, x tick, y tick, z tick. Lorentz considered the simple case when one frame moves with respect to the other at a constant velocity v, but if one frame accelerated with respect to the other, the theory became untenable. This is the famous Lorentz transform. The spacetime used by Lorentz is known as flat spacetime, meaning that it is described by a certain limit of more general geometry. Flat spacetime is described by a simple metric known as diag 1 minus 1 minus 1 minus 1, a 4x4 matrix with these numbers on its diagonal. Lorentz, Poincaré, Voigt and many others applied the theory of special relativity to electrodynamics and found that the Maxwell Heaviside equations obey the Lorentz transform and were therefore thought to be equations of special relativity. The Newtonian system of dynamics does not obey the Lorentz transform. There is no limit on the linear velocity in the Newtonian system. So there developed a schism between dynamics and electrodynamics. They seem to obey different transformation laws on different geometries. Dynamics have been described for 2 centuries since Newton by the best minds as existing in Euclidean space and time. Electrodynamics existed in flat spacetime. The underlying geometries of the 2 subjects seem to be different. Attempts were made around the turn of the 20th century to resolve this fundamental challenge to physics. Einstein in 1905 applied the principles of Lorentz to dynamics using the concepts of form momentum, relativistic momentum, and energy. The laws of dynamics were merged with the laws of electrodynamics, using c as a universal constant. Einstein also challenged dogma, and many scientists of the old school rejected special relativity out of hand. Some dogmatists still reject it. From 1905 onwards, physics ceased to be comprehensible without mathematics, which is why so few people understand physics today and are easily deceived by dogmatists. At the end of the 19th century, several other flaws were found in the older physics, and these were resolved by quantum mechanics, notably by Planck's quantization of energy. Quantum mechanics seemed to give an accurate description of black body radiation, the photoelectric effect and the specific heat of solids, but departed radically from classical physics. Many people today do not understand quantum mechanics or special relativity because they are completely counterintuitive. Planck, Einstein and many others, notably Sommerfeld and his school, developed what is known as the old quantum theory. The old quantum theory and special relativity had many successes, but existed as separate theories. There was no geometrical framework with which the 2 types of theory could be unified, and special relativity was restricted to one frame moving with respect to another with a constant velocity. The brilliant successes of the classical Newtonian physics were thought of as a limit of special relativity, one in which the velocity v of a particle is much less than c. A new corpuscular theory of light emerged in the old quantum theory, and this corpuscle was named the photon about 20 years later. Initially, the photon was thought of as quantized electromagnetic radiation. In about 1905, physics was split 3 ways, and the work of Rutherford and his school began to show the existence of elementary particles, the electron having been just discovered. Einstein, Langevin and others analyzed the Brownian motion to show the existence of molecules, first inferred by Dalton. The old dogmatists had refused to accept the existence of molecules for over a century. The Rutherford Group showed the existence of the alpha particle and inferred the existence of the nucleus and the neutron, later discovered by Chadwick. Rutherford and Soddy demonstrated the existence of isotopes, nuclei with the same number of protons but different number of neutrons. So physics rapidly diverged in all directions. There was no unified theory that could explain all of these tremendous discoveries. Geometry, in the meantime, had developed away from Euclidean principles. There were many contributors. The most notable achievement of the mid-19th century was that of Riemann, who proposed the concept of metric. Christoffel inferred the geometrical connection shortly thereafter. The metric and the connection describe the difference between Euclidean geometry and a new type of geometry often known as Riemannian geometry. In fact, Riemann inferred only the metric. The curvature tensor or Riemann tensor was inferred much later in about 1900 by Ricci and his student Levi-Civita. It took over 30 years to progress from the metric to the curvature tensor. There was no way of knowing the symmetry of the connection. The latter has one upper index and two lower indices, so is a matrix for each upper index. In general, a matrix is asymmetric, can have any symmetry, but can always be written as a sum of a symmetric matrix and an antisymmetric matrix. So the connection for each upper index is in general the sum of symmetric and antisymmetric components. Christopher Ricci and Levi-Civita assumed without proof that the connection is symmetric in its lower two indices, the symmetric connection. This assumption was used by Bianchi in about 1902 to prove the first Bianchi identity, from which the second Bianchi identity follows. Both these identities assume a symmetric connection. The antisymmetric part of the connection was ignored irrationally or dogmatically. This dogma eventually evolved into general relativity, an incorrect dogma, which unfortunately influenced thought in natural philosophy for over a century. The first physicist to take much notice of these developments in geometry appears to have been Einstein, whose friend Grossman was a mathematician. Einstein was not fond of the complexity of the Riemannian geometry as it became known, and never developed a mastery of the subject. After several attempts from 1905 to 1915, Einstein used the second Bianchi identity and the covariant Noether theorem to deduce a field equation of general relativity in late 1915. The field equation was solved by Schwarzschild in December 1915, but Schwarzschild heavily criticized its derivation. It was later criticized by Schrödinger, Bauer, Levi-Civita and others, notably ECE Cartan. Cartan was among the foremost mathematicians of his era and inferred spin-laws in 1913. In the early 20s, he used the antisymmetric connection to infer the existence of torsion, a quantity that had been thrown away 20 years earlier by Ricci, Levi-Civita and Bianchi, and also by Einstein. The entire theory of general relativity continued to neglect torsion throughout the 20th century. Cartan and Einstein corresponded but never really understood each other. Cartan realized that there are two fundamental quantities in geometry, torsion and curvature. He expressed this with Moore in the form of two structure equations, and using a differential geometry developed to try to merge the concept of spin-laws with that of torsion and curvature. The structure equations were still almost unknown to physics before they were implemented in 2003 in the subject of this book, the Einstein Cartan Evans unified field theory known as ECE Theory. The ECE theory has swept the world of physics and has been read and accurately estimated 500 million to 1,000 million times in 11 years. This phenomenon is known as the post-Einstein paradigm shift, a phrase coined by Alwin van der Merwe. The first and second Moore-Cartan structure equations can be translated into the Riemannian definitions of respectively torsion and curvature. The concept of commutator of covariant derivatives has been developed to give the torsion and curvature simultaneously with great elegance. The commutator acts on any tensor in any space of any dimension and always isolates the torsion simultaneously with the curvature. The torsion is made up of the difference of two antisymmetric connections, and these connections have the same antisymmetry as the commutator. The connection used in the curvature is also antisymmetric. A symmetric connection means a symmetric commutator. A symmetric commutator always vanishes, and the torsion and curvature vanish if the connection is symmetric. This means that the second Bianchi identity used by Einstein is incorrect and that his field equation is meaningless. The opening sections of this book develop this basic geometry and use the Cartan identity to produce the geometrically correct field equations of electrodynamics unified with gravitation. The dogmatists have failed to achieve this unification because they used a symmetric connection and because they continued to regard electrodynamics as special relativity.